In this tutorial, we want to think about how to calculate the travel time for a tsunami to reach a point of interest, for example, the coast. And to do that, we're going to use a combination of data recorded for the Japan Tohoku tsunami at several of the DART buoys, the tsunami buoys out in the ocean, and from that we'll be able to calculate how much time there was before the tsunami hit land. Now to do that, we have these DART buoys, and they're recorded in a variety of places in the ocean. The figure here shows the region, and we have some formulas or some mathematics that describe them. In particular, we're going to use this DART buoy that's located very close to the epicenter, the first one shown in the top right here. And if we look at a blow-up version of that, and this you have in your package, we see the actual record that was recorded there. The red line is what was calculated using the same approach we're going to use. The black line is what was actually recorded. Now, a couple of key things. The axes are given in terms of amplitude of the wave in meters on the y-axis. The x-axis look at is in hours. And so this is 60 minutes, 120 minutes here, etc. Two other things to see. There are actually two different types of earthquake-related waves being recorded. These first set of waves here are the actual earthquake, the shaking with the earthquake, which caused the sea bottom to move up and down, and that's recorded on the device. But important to us is this time right here, which is when the tsunami wave reached this point. And so we can make that, and we can measure and see how many minutes it was between the earthquake, which is at the 0 point, and the tsunami reached our DART buoy. And we have a cross-section that shows where that DART buoy is, and this is also in your packet. So the DART buoy is located here at the far end of the plot. So the buoy would be right here. The earthquake is occurring somewhere in this vicinity here, and so the distance from that to the buoy will be the distance from here to there. Similarly, we have the shoreline here, and we're going to be interested in how long it takes for the tsunami to get from here to there. So we're going to do both of those calculations. But to do that, we need to first look at the physics of the problem. And tsunami waves, being waves, have formulas that look like many other waves. We will write this as follows. C is equal to the square root of GL over 2 pi times the hyperbolic tangent of 2 pi d over L. Now in this, L is the wavelength of the wave, and d is the water depth. And this is called C because it's actually the celerity, which is the velocity of a wave. And remember, water waves, as they pass by, they don't actually, the water doesn't move by, you just have the energy associated with the wave move by. And so this C is the celerity. It's like in Einstein's formula, you have E equals mc squared, because the C there is the calculations you would get for the speed of light, which is treated as a wave. Now this is a little bit complicated. In particular, it has this hyperbolic tangent, and most of us don't have that function on our calculators we have, unless you have a fairly complex one. However, it ends up that because of the way the hyperbolic tangent behaves, if the water depth is much less than the wavelength, that is, it's less than 1/20th of the wavelength, then this formula turns into a much simpler one, which says that the wave velocity is simply equal to the square root of g, which is gravity, times the water depth. And so that's very easy to do. And it ends up that for most tsunamis, this is on the order of 200 kilometers or more. And since the seafloor is typically in the 3 to 4 to 5 kilometer depth range or less, we see that we meet this criteria quite good, because there's virtually nowhere except in the deepest trenches where the water depth is 10 kilometers or so. So this is the formula we can use, and we want to, before we use it, to calculate the velocity to the shore, which is really what we want to know, how much evacuation time would there be, we can test it by saying we know when it actually did reach the dart buoy. It got to the dart buoy approximately, something like 30 minutes. Now you want to make your calculations more precisely, but it's somewhere in the 25 to 30 minutes that it took, and we have the water depth. We know what the water depth is along most of the path, and so I can look at that. I can look across, and the water depth is something on the order of, I don't know, I'll just call that 5,000 meters or so. It's a little more than 5,000 meters, but I'm just doing a rough estimate here. You'll want to, again, be a little bit more precise. So if I look at that and say the water depth is about 5,000 meters, and the distance it traveled is about like that, I can then do a calculation. If I know the velocity from here to here, and I know the distance, I can figure out the travel time. So to figure out that velocity, we would simply plug in these numbers. So if I say that c is equal to the square root of g times 5,000 meters, that's the same as the square root of 9.8 meters per second squared times 5,000 meters. And to simplify things a little bit, I'm just going to assume that this is equal to about 10. And so I have that c is equal to the square root of 50,000 meters squared per second squared. And that's going to be equal to then about approximately 220 meters per second. So that's pretty fast. Most of us can't run at 200 meters a second, and we can then convert that into miles, kilometers per hour, whatever, but we can then also calculate how long it would take at that rate for the wave to reach this spot here that we know to be about 30 minutes. And if I look at that and I say, okay, this is about 630,000 meters, and this is about, let's just call it 200,000. So I'm just going to roughly say it's about 400,000 meters. So about 400,000 meters divided by 220 meters per second. Cross out a few things here. So I have 22 going into that. That goes in about, that's about 2 times. So now I have 2,000 seconds, and that's going to be equal to 2,000 seconds divided by 60 seconds in a minute. And that's going to be something like 32 minutes. So I see that even in this rough calculation, and of course in your assignment you should do it more precisely, I'm getting approximately the right number. So we now can see that the formulas seem to work pretty well, and what we want to do is now calculate the actual time it would take for the wave not to reach the buoy as we have here. We have that data. We want to know how long it will take to reach the coast, so we want to know how long it takes to travel that distance, or in fact right to the coastline. And the main thing we have to worry about here is the fact that in contrast to the buoy, where the water depth was about constant, the water depth is changing a lot here. So we don't really have a single value for water depth we can use, but rather we can break this up into sections perhaps and treat it as, for example, maybe 3 segments, each with a different water depth, and then we would calculate that. So we would pick this water depth, calculate the velocity for that, and figure out how long it would take to travel that distance. Then do the same for this location and that location, and then add them all together. That's what you're being asked to do in the assignment, to figure out how long it would take for the tsunami wave to go from the source out by the trench to the coastline. So that's the first part of our assignment, and I'll stop the tutorial for that now, and the second tutorial will be calculating the height of the tsunami when it reaches the shore.